Today we will discuss about the rolling loads, unit 5 of your syllabus. First we will see what are the rolling loads, and then we will also discuss the difference between the rolling loads and influence lines. So first, what are the rolling loads? They are nothing but the common type of rolling loads are the axle loads of moving trucks or vehicles. They can be also the wheel loads of a train, or even the wheel loads of the gantry assembly on a gantry girder. The gantry assembly is nothing but it carries the heavy materials from one side of the building to the other side of the building. Okay, or that is why the gantry assembly moves over the girder. So how the loads get transmitted from one end of the girder to the other end of the girder is taken into consideration here. And then we also will discuss about how to determine the shear force and bending moment at different sections as the load will traverse from one end to the other end. While solving the problems, the magnitude of load given in this problem is taken to draw the shear force diagram and bending moment diagram. On the contrary, what happens in influence line diagrams is the load will be taken as a unit load. That means 1 kilonewton will be considering. Okay, so here influence line diagram is nothing but again a curve or a graph that will represent the function like a reaction at a support. So when we are discussing about the reaction at the support, we will be only considering the unit load will move from one end of the beam to the other end of the beam, and the reactions at the supports will be calculated. Similarly, when we take the function of shear force, what we will do when the unit load again is moving from one end to the other end of the beam, we will calculate the shear force at different locations. And also the same thing is done for the bending moment. Okay, so at different positions of the unit load, we will be estimating the bending moments and also the shear forces at different locations. Okay, and then we will draw the influence line diagram that will be for shear force separately and for bending moment also separately. Okay, so after that, what we can do is we can calculate the required ordinates. The ordinates will be computed based on the unit load that moves, and then we can multiply that ordinate with whatever is the magnitude of the load given, so that we can get the shear force at that particular location. So here in rolling loads and influence lines, we will be discussing the following cases. We have 5 cases here. Firstly, we will discuss about the single concentrated load, and then the uniformly distributed load, which is shorter than the span, and we have one more case there, that is uniformly distributed load longer than the span. Then we also have 2 concentrated loads spaced at some distance apart. Now here then we have a series of concentrated loads. Now when I say here single concentrated load, it will be usually the pedestrian when he moves from one end of the beam to the other end of the beam. That is how it is considered. The load of the person will be taken as a point load. Next, uniformly distributed load shorter than span. There may be IRC track loads. Uniformly distributed load longer than span, when the vehicle is of a span greater, like especially there can be train of loads, and then we have 2 concentrated loads spaced at some distance apart. Now this will be usually the two-wheelers. The two-wheelers 2 axle loads will be taken as the 2 concentrated loads, where the distance between these 2 loads is constant. Then we have a series of concentrated loads. Now when I say series of concentrated loads, it can be the truck where the more number of axles are there, and they are at a definite distance apart between them. Okay, so we will discuss all these for rolling loads first, and then we'll go for the influence line diagrams. Okay, so first, before going to these cases separately, we will first discuss some important definitions. So first of all, in this chapter, we will be dealing with something that is called as absolute maximum bending moment in a beam. Now where will the absolute maximum bending moment exist, and how to determine it? So that for that, these are the certain conditions. When a given load system moves from one end to the other end of the girder, depending upon the position of the load, there will be a maximum bending moment for every section. So as the load moves from one end, that is left to the right of the girder, there are going to be n number of bending moments, So amongst them, at a particular location, we are going to get one maximum bending moment. Okay, so the maximum of these bending moments will usually occur near the mid span. Okay, so when the load is very near the mid span, we are surely to get a maximum bending moment. Okay, so the maximum bending moments will be taken as the absolute maximum bending moment. Okay, now here there is one simple case with example we have just discussed how to find the location of the absolute maximum bending moment. So where do we have the absolute maximum bending moment? In a simply supported beam when a series of wheel loads cross it. So here I have considered a series of wheel loads. WCR is taken as one of the heaviest loads. Okay, so when a series of wheel loads crosses a simply supported beam, the absolute maximum bending moment will occur near the midspan under the load WCR. WCR is the heaviest load which is nearest to the midspan. So under that load we are going to get the maximum bending moment. Supposing there is one more case here. If WCR is placed at one side of the midspan C, either at the left or to the right, okay, then what happens is the resultant of the load system R shall be on the other side of C, and WCR and R shall be equidistant from C. So you can see that in this figure here. So you can see there the distance between WCR and R is equidistant from the center. So this should be the position of the load. Then we will get maximum bending moment under WCR. Okay. Next, one more case can exist like this, where the WCR, that is the heaviest load, will coincide with the resultant. Okay. So under that case, what will happen? We will get the maximum again bending moment under the midspan only, at the midspan. Okay, so here you can see that WCR is coinciding with R, that is the resultant of all the loads. Okay, so therefore we will have again the maximum bending moment under the WCR. Okay, so like this we can calculate the absolute bending moment at different locations for different types of loadings. Similarly, again we have one more case here, that is UDL longer than span. In that case, where the absolute maximum bending moment is there on a simply supported beam. When a simply supported beam is subjected to moving UDL longer than span, the absolute maximum bending moment will occur when the whole span is loaded. Okay, and M max will be your WL square by 8. This is similar to that of your simply supported beam loaded with UDL throughout the length of the beam. Okay. Now state the location of maximum shear force in a simply supported beam with any kind of loading. Now here there are two cases when we discuss about the shear force. You will have one positive shear force and another negative shear force. So where do the positive shear force exist and where do the negative shear force exist? We need to see that. So here there is a thumb rule. It says that in a simple beam with any kind of load, the maximum positive shear force occurs at the left hand support, and the maximum negative shear force will always occur at the right hand support. Okay, so then we have one more thing. What is meant by maximum shear force diagram? Now here basically we are interested in the shear force diagram and also the bending moment diagram. So first we will see how we are going to find out the maximum shear force due to given load system, whatever may be the given load system. Okay, for that the maximum shear force for every section of the girder can be worked out by placing the loads in appropriate positions. So by moving the load, we will try to find the shear forces and then try to locate which is the maximum shear force. So then when these are plotted for all the sections of the girder, then the diagram that we obtain is the maximum shear force diagram. So this diagram will give us the design shear for each cross section. This design shear will be helpful in RCC design. Next, what are the uses of influence lines? Now after the rolling loads we will be also discussing the influence lines. Now why is it required? So influence lines is very useful in quick determination of reactions. At any location you will be able to find out, placing the load at any location you will be able to find out the reactions. Then also the shear force at any point on the beam will be able to locate. Even the bending moments can be estimated or similar functions at any given section under any given system of moving loads can be determined using these influence lines. They are also useful in determining the load position to cause maximum value of a given function in a structure on which the load is placed. Okay, and it can vary from position to position. Now before starting with again the derivations and all, here the sign conventions I would like to discuss, wherein how the shear force sign conventions are adopted. We have previously been adopting the same sign conventions, still we'll discuss it here. What is a shear force sign convention? A shear force in a downward direction to the right hand side of a section or in an upward direction to the left hand side of the section will be considered as positive. Similarly, a force having an upward direction to the right hand side of the section or downward to the left hand side of the section will be considered as negative. Okay, so and also the bending moment. For bending moment, the sagging bending moment is considered as positive, whereas hogging bending moment is considered as negative. So one more thing I would like to clarify here. In case of sagging bending moment, the top fiber will be in compression. So you can see here the top fibers will be in compression and the bottom fiber will be in tension. With respect to the neutral axis, this is with respect to the neutral axis. Okay. In case of hogging bending moment, the top fiber again here will be in tension and the bottom fiber will be in compression. Okay. So this type of a behavior, that is sagging bending moment behavior, will be in simply supported beams, and hogging bending moment will appear in the cantilever beams. Okay. So with this, I think this part of discussion is sufficient. We will next go for the part 2, where we will be discussing the single concentrated load, the derivation for it, and also the derivation for uniformly distributed load, which is shorter than the span. Okay, thank you.